Next speaker is Rui Castro from Eindhoven, and he's going to be speaking on are there needles in a moving haystack?
Okay, well, thank you for the invitation to be here. It's a great, great workshop and great program. Also, thank you for the organizers of this workshop and the entire program. So this is joint work based on joint work with Ervin Tánczos, which was a PhD student in Eindhoven and is now in UW Madison. Okay, good. So the motivation is that there are many situations where, well, you might try to measure something, collect observations about a process, and the process is changing while you're measuring it, right? For instance, you want to detect covert communications. There's an enemy or whatever trying to communicate over the electromagnetic spectrum. They change channels. They do it at channel 1 for a little bit and then change to channel 8 and so on. And you like to, well, to see if there's anyone there or not, for instance. Or you're trying to detect diseases hotspots, like you have a rapidly spreading disease or a disease that has a very, rapidly spreading, let's say, and appears here and there and there and there, and you cannot see it everywhere, so you'd like to know if something is there. Actually, another motivation came from a colleague from industry, from Philips Lighting Research. They want to essentially detect people inside buildings and decide what to do with the lights. Okay, so how difficult is it to see a moving target? That's the main question. And of course, we are not the first ones to look at this, right? Obviously, in Russia, someone had looked at this in the 60s. So they look at a different problem, but it's in this spirit, and this is kind of follow-up work on that. And there's also problems related to essentially change point detection that are somewhat related. But our setting here is a little bit different. So let's do a little bit of a motivation. So let's say you have a structure like this, like a graph, and at time 1, maybe these two nodes are active. Maybe at time 2, same thing happens. At time 3, one of them moves to, well, somewhere close to the neighborhood, and so on. It keeps, the process evolves like this, right? And, okay, obviously we don't observe this. We only have access to partial and noise information about this process, right? So actually, all we get to observe is we get to look at one node at a time. Maybe you can generalize it to a small subset of nodes, but okay, you look at one node at a time, and you measure if it's active or not with some amount of uncertainty or noise, right? Maybe here you measure this one, it seems, oh, maybe something is going on. Maybe you measure it again and again. Like, oh, maybe I'm almost ready to say that with some degree of confidence something is there, but, well, maybe the signal disappeared. Maybe you measure it one more time. Well, maybe I was just hallucinating it, and so on. So this is what we would like to try to understand. Okay, how difficult is this problem? So let's try to formalize it a little bit. Okay, and it's going to be a very simple model because we are just trying to understand what's going on here. So it's not going to be necessarily very practical. Right? So time for us is going to be discrete, 1, 2, 3, 4, etc. And the signal of interest is going to be a vector, an n-dimensional vector, and it's going to be a sparse vector, right? So it's going to, most of the entries of the vector at any time are going to be 0, and some of them are going to be valued mu, have an elevated mean, where mu is greater than 0. And S of t is the support set of the signal, okay? And so the idea is that these models, each entry of the vector models, for instance, the activity level of a certain node in a network or a channel, something like that. Good? So, and just for sake of jargon, right, the signal components in ST are what we call the active components, right? And the model seems a bit restrictive because, okay, all the active components have the same magnitude. Well, you can actually consider different magnitudes and different signs, and you can still do more or less everything we do, especially in the regime we are going to consider, where we are not going to take too many measurements, right? And then actually this is pretty much the worst case scenario, and any other characterization is going to involve this. Okay, good. And as I said, we are interested in sparse signals. Good. So what do we observe? So this is the general structure of the signals. I haven't said anything about the dynamic behavior, how the signal evolves over time. What do we observe? So it's essentially like a normal means model type thing. We observe m noisy coordinate-wise measurements of the signal. So at each time, we can choose one entry to measure, a of t, right? And then what we observe is, well, that entry plus some noise. That's it. Right? And the noise, the additive noise in the observations is independent. Okay. And of course, once you get to this point, you see that there is a lot of flexibility how to choose your experiments, how to choose your design, A of t. Right? You can do essentially one of two things. You can do what we like to call adaptive sensing, but sequential experimental design would be the more old school statistics term, right? So you can choose A of t as a function from the past, so from all the observations y of j and a of j from the entire past, you can choose this, and of course you can use some intrinsic randomization in this design. Right? So this would be adaptive sensing. Or you can do it in a non-adaptive way, which essentially means that you should decide where to measure things before you start collecting any observations, right? And clearly this is more restrictive than that, so you should expect this to do something a little bit better, at least. Okay? Good. Clear so far? Good. So now we have a signal model, we have the observations. So what do we want to do with this? Right? We just want to do an hypothesis test. We want to solve a detection problem. Okay? We want to answer the question if there's needles in this moving haystack. Right? So we want to test this hypothesis, and the alternative hypothesis here is not yet very well specified. I will do that later. Right? So the null hypothesis is that there's no signal there. There's nothing there to detect, right, at all times. And the alternative is that there is something there. Okay? And I'll specify this later on. Okay? And so a bit more formally, so what we want to do is you take all the observations, essentially are places where you measure things and the corresponding observations, and we just want to make a binary decision, right? Phi at, and we measure the performance of that decision in terms of the worst case type 1 and type 2 error. We want essentially those two errors to go to 0. So we can look at this. Could also look at the sum. Maybe we should have done it with the sum. It would be maybe cleaner, right? So we want the risk, which is essentially the worst case of the type 1 and the type 2 error. We want it to be small, right? Smaller than some epsilon. Okay. So here, just for sake of notation, although P of I is essentially the distribution of pretty much these things under the null and under the alternative. Okay. So at this point, I still, if I want to do something here, right, I probably want to try to say something about, okay, what can I assume about the signal dynamics, right? What's going on there, right? So what is known if actually the signal was not changing? It stayed put for the entire measurement period. Okay? So in that case, right, you have signal support is not changing over time, stays fixed. Let's say there's only little s components out of n, and let's say little s is small, right? Well, if you are in the normal means model, right, you would make exactly n measurements. You have n signal components, you make exactly n measurements, right? And there is a lot of work going back to Inkster that will tell you that, well, if you want the risk to be smaller than epsilon, your signal magnitude needs to scale roughly like a constant times square root of log n over s squared. And figuring out that constant is not what is the right constant is not easy, and that's mainly due to Inkster to figure out, okay, the different regimes where and get much more refined bounds. Right? Of course, in general here, I don't want to restrict myself to the case where I have exactly n measurements. I might have more or less measurements. Right? But it turns out that to solve our problem, this is actually not a very good idea, even if I have m measurements. Okay? If I want to detect the signal, I should not just measure all the components. Right? It turns out to be much better to do a sort of a subsampling scheme. instead of measuring everything, before you've seen any signal, you select a subset of the components that you're going to measure in, and you'll measure them multiple times. Okay? So essentially you select about n over s randomly chosen entries, so which means you only see one active component in that set, or a constant number of active components, depends on the constant you put there. And you'll measure each component that you chose in this subsampling scheme multiple times, s over n times m. And if you do this, right, the risk will be smaller than epsilon, provided signal magnitude is larger than something like this, right? And I'm interested in regimes where n over sm, so m is something around the order of n, or n over s, roughly around that case. So this is what you know. So you can do it better than uniform sensing. Okay, it's not so special. What if you do adaptive sensing? Well, if you do adaptive sensing, you actually can do significantly better. Essentially, you can drop this dependence, this algorithmic dependence on the extrinsic dimension on n, and still be able to detect the signal. So you can really focus on what's going on. Right, so these two things, if I'm thinking out the regimes that I'm interested in, these are essentially like a constant, so this could be a significant difference. Right?
Are these lower or upper bound?
This is a lower bound. This is well, it's upper and lower bound. Essentially, up to constants, this is really the minimax. And there is a method that achieves this as well. Good. So let's now try to put dynamics into the picture. Okay? So when we started this, okay, well, let's think of what is the easiest way to go from this static case to a dynamic case and ways to interpolate around. And we thought about this model that it's probably the simplest one we can think of, right? So the idea is that we'll have a parameter, p, could be 0, could be 1, could be anything in between, that sort of controls the rate of change of your signal. Right? So at time 1, let's choose to support uniformly at random from the class of sets of size s. Right? So something like this, right? And then what you do after that? Well, for each active component, you flip a coin. Okay? And with probability 1 minus p, it will stay put. It will stay there. It's not going to move. With probability p, it will change. It will move somewhere. Right? So essentially, you flip a coin. This guy will stay in the same place for the next time slot. This one will stay. The other ones will move. And essentially, they will just move to any location available. Right? So it might happen, just by chance alone, that this guy ends up in the same place. Right? So, but that's the model. And you just keep doing this. Right? Just in this case, only one component moves, and so on. Good? So that's it, right? So this is a bit more formal here, but it's not really needed because I'm not going to go into the very nitty-gritty technical details of the proofs. But the key thing to notice is that this parameter, p, controls this rate of change, right? So if p equals 0, it's a static signal, nothing changes, right? And if p equals 1, the signals will be essentially independent at each time, right? Everything resets from time to time, right? Right. But what's interesting is what's happening in between, right? And what do these signals look like? Well, if p is small, right? This is time. This is the signal component. So of course, this is a very small problem. You see that components can stay put for a while, and then they move around. So you'll get something like this. So you see there's a lot of structure. And if p is a bit larger, you start having less and less segments of contiguous activation. And at some point you have nothing, or almost nothing. Good. Okay. So now I can be maybe a bit more specific about the alternative I want to consider, right? I want to test that, well, you know this, there's no support, or I could state this as mu equals 0, there's no signal magnitude. And here I have a signal with the dynamics I just described. And the question I would like to ask is, okay, how large must the signal strength be, mu be, to ensure that the risk is small, right, for some epsilon. Okay? And I don't want to get necessarily asymptotic results, so I want to answer this question. And what are the ingredients I have here? What are the quantities of interest, right? I have signal strength mu, that's what I want to characterize, as a function of, well, signal dimension, the sparsity S, the speed of change P, and the total number of measurements. Okay? So I think one of the talks yesterday or the day before mentioned, well, typical setting of minimax. You have a bunch of things, let's just shove it together and get some rates. Okay, so let's first just think of the number of measurements. Well, in this problem, actually, you get very little information for each one of the measurements because you measure one signal component at a time, right? So it's clear that even if you were in the best possible scenario, just by chance alone, you can not sample an active component if you take very few measurements, right? So pretty much very obvious, right? If you take less than n over s measurements, right? Just by chance alone, you will not sample an active component. You will not collect any observations that have any signal, right? That probability will be bounded away from 0, like essentially 1 over e or something like that. So in order to hope for anything, we have to have the number of measurements to be at least some large enough constant times n over s, right? So the number of measurements m must be at least as large as a function of epsilon. If you want the risk to be smaller than epsilon, that the number of measurements has to be at least as large as c epsilon times n over s. Otherwise, there's no hope, right? So and this is what we call the small sample regime, and most of the results I'm going to present here are, well, some of them apply outside this regime, but they are only interesting in this regime, right? And it would be interesting, it would be good to have an answer for, well, other regimes, but if you're interested in detecting signals quickly, this is the regime you are going to be in, right? You want to sample and make a decision as quickly as possible. And in some of these problems, actually, this is what you want to do. You want to quickly find out if something is going on. Good. So we are going to focus on this situation. Okay. So let's see what we can do. Okay. So let's come up with an adaptive sensing approach. And it's going to be super easy. Okay. Recall that our observations, right, given your decision to measure component A of t, are just a sample from a normal, right? Either with an elevated mean, if it's an active component, or 0, right? Let's make it even easier. Let's suppose there is no noise, right? So essentially, if you hit a active component, you observe mu, otherwise you observe 0. So then what can you do? Well, it's pretty obvious what you have to do, right? The only sensible strategy is just to sample, essentially at random, but without replacement, components, signal components, until you see something, right? So you have your signal here, maybe you measure here, you didn't see anything, let me just measure another component, nothing, nothing, until you hit something, in this case here, right? And then you're done. So if you exhaust your budget and you didn't see any active component, you say, okay, I cannot reject the null hypothesis. Otherwise, I would say, well, I do reject the null hypothesis. Right? So what we have to do is take this and somehow deal with the noise. Right? So what can you do if there's observation noise? Well, essentially what we did, that we used also in our previous work when we were looking at structured sparse signals, is essentially to look at what you do if you have no noise and then robustify that procedure, right? So you just replace each one of these sort of noisy queries, noisy samples that noiseless queries you were trying to make, by a sequence of observations. Okay? Very much in the spirit of the sequential likelihood ratio test of Wald. Okay? So we have a different procedure, a sequential thresholding test, but it's similar in spirit. Okay? So each component you select to measure, right, it's sampled repeatedly until you can make a decision if you think it's active or it was active or not. Right? And what's the main challenge, the main difficulty here is that, well, the level of activity of a component can change during the measurement period, right? So you might start measuring it and it's active and then it stops being active. So you need to guarantee to characterize what happens in that case. Okay? So in a nutshell, what is the sort of the algorithm or the algorithmic idea? You make a total of t queries. So you just choose, okay, I'm going to choose t signal components that I'm going to measure, and you just choose them uniformly at random, right? And I'll tell you what t is going to be in a little bit. And for each one of these, right, you just do this sequence of observations. And this test, well, if the test deems that there's an active component, you say you reject the null. Otherwise, you run out of measurement and you just say I cannot do anything. So it looks like this, right? So let's say you take this measurement, you decide, okay, I'm going to measure it again and again, and this sequential thresholding test will decide at this point maybe it's not worth keep measuring it, so let me switch to the next query, and you just do this. And maybe here you measure something that's active again, you measure it again, but maybe there's still enough evidence to declare that that there was an active component there, and you're done. Yeah?
So in the static case, it would seem to make more sense to at least sample without replacement.
Yes.
But
this just makes it easier, and the signal is sparse. So I'm thinking of S to be little o of n or something like that, and then it doesn't really make a difference, or little o of n over log n, and then this does not make a difference. It just makes the analysis a bit easier. Okay, so what is the sequential thresholding test? Okay, it's there's many parameters, so it looks a bit complicated, right? But it's kind of on one hand a poor man's version of the sequential likelihood ratio test. One good thing is that you don't need to know mu to conduct this test. So it's strictly speaking not the same thing. But essentially you are going to make at most k measurements. And what you do at each time, you compute the average of the measurements. And if they are below a certain threshold here, then you declare no signal. If that average is really small, small enough, you declare no signal, you stop. You don't collect more measurements, so you stop early. If the average is very large, larger than this threshold after the first measurement, this threshold after the second measurement, and so on, you declare there is a signal. Otherwise, you just continue until you run out of samples. Okay? And of course, how do you pick these thresholds and so on? Well, it's going to look messy because it's just copied from the paper. Right, so I don't expect anyone to read this. Well, maybe in the paper, not in the slide, right? But so we take essentially log t at most log t measurements. We choose the thresholds in this funny way, and what are the guarantees we give, right? So if you are under the null, right, this test, each one of these tests will essentially make a type 1 error, give a false alarm, declare signal with probability at most epsilon over t. Right? If you are under the alternative, right, it will essentially make an error, essentially not see that there's a signal there, so a type 2 error. If the signal magnitude with a small probability, epsilon over 3, if the signal magnitude is larger than this, right? And this holds, so you see there's a J here, right? So if your signal is active only for like 2 observations, you need a bigger magnitude. If it's active for a longer time, you need a lower magnitude. So this result holds for any J. So your signal can be active and then disappear, and you still can guarantee this. Okay? So that's the main idea, right? And so essentially, this is the main aspect of getting this to work, right? So, and you have to have the test guaranteeing that even if the signal disappears, you can still say something meaningful. Right? So when you put all this together, what you'll get is a result like this. So if your signal is sparse, little o of n over log n squared, right? If you choose to make, well, this many number of measurements, so it's a function of epsilon times n over s, right? Then the risk of this specific test I described is smaller than epsilon, provided signal magnitude is larger than this, right? And this contribution here, right, that there, it's the same that you get if you have a static signal, right? So it's that results for adaptive sensing for static signals. And this is what happens because of the dynamics, right? So, and maybe it's not as digestible here, right? So I have a factor here, tau. So if tau is greater than 1, you're okay. If tau is below 1, we cannot prove that this works, right? So if the rate of change p, which I can make here as a function of n if I want, if the rate of change is larger than this, right? If it's not too small, too close to 0, essentially it means that the signal magnitude needs to scale like square root of p times log n over s in order to be for it to be sufficient for this algorithm to do signal detection. So maybe in more digestible terms, well, let me see if I have it here. No, okay. So that's what it means. So this highlights the role of this dynamic in this problem, right? So maybe some remarks. So if p is very small, you are essentially back in the static case. It's not exactly like that, but you are essentially in the static case. So that's that second term that we have there. If you are in the extreme case that p is equal to 1, well, essentially each signal realization is independent from each other, right? So you are pretty much in the sparse mixture case, right? So actually in that case, the problem is just testing for, you have observations from IAD observation from a standard normal, or from a sparse mixture where the mixing coefficient is s over n, right? And you know in that case that it suffices to have signal magnitude scaling like this, which is precisely what we have in that result. So this sort of ties in what happens in between. Good. So yeah, this is not so important. The result, the analysis is valid for any number of measurements, but of course it's not very interesting if the number of measurements is very large, because we can come up with a global test that is better, right? Yeah, you can only get this type of performance because of adaptive sensing, and the proof, well, it's just controlling the chance of anything bad happening, right? So there's nothing really special or like technically challenging there. It's just going through the motions using some concentration inequalities and so on. Good. So summary so far, right? So you have this small sample regime, right? If you want conditions on the risk to be small, sufficient conditions are what I just highlighted, right? So if the signal is static, signal magnitude needs to be larger than a constant. Otherwise, it needs to scale like square root of p log n over s. Okay. So let's try to fill out essentially this table and also get necessary conditions. Right? Let's start with non-adaptive lower bounds, right? So if you are doing non-adaptive sensing, right, you have to essentially select where to measure things before you start. Okay? So what you get, again, is a bit undigestible because it was just copied from the paper, right? But if you want to risk to, and it just, one thing that I should notice, it just deals with two extreme cases, the static case and the completely non-static case. So in the static case, well, in this case, it's just a sparse mixture case, so we derived it in a non-asymptotic way, but you recover the results that were already expected, right? In static case, you get this. So written in a more palatable way, you get essentially this result. And this is a little bit different than what you see in Inkster and the work of Inkster and Suslina, because here we are saying, okay, you can consider any design that you want, as long as it's non-adaptive, any design you want, and so it could be the subsampling, could be uniform sensing, and so on. And this is the best you can do. Okay? And this is just a sparse mixture case, right? So in the small sample regime, right, what you get is essentially this, right? And you see that these two terms look about the same. There's a difference between an s squared there and an s, which is actually that s square. I don't think it should be. Sorry, that that s square should not be there. Actually, I don't think, but I didn't manage to. We did manage to work this out in the proof. Okay. So they are almost the same regardless of p, right? So what about, yeah?
That's a question about that. So I'm just trying to think about the case where n and s are both equal to 1. So there's only one thing, and it's either mean 0 or not, and you have to decide. And if you give me a certain amount of time, you know, like I'm just going to keep measuring and accumulating it, and then I'd get the random walk, and I'd have some LIL type of thing, and I'm just wondering where's that iterated log, or why isn't it there, or
Well,
is it hiding something?
Yeah, a little bit. Well, first of all, you are looking at sort of this regime, n over s, so you have only a small number of measurements. You cannot make this number of measurements grow,
Yeah.
right? So it will, in that case, it will be a constant. And let me see if I have it stated here. I have this statement here. That also
M is the number of measurements you make.
m is the number of measurements. S should be less or equal than n over 2. So
So I'm sort of thinking it should be something like square root of log m
Yeah.
over m.
and this is lower bounds and the constants here. So I'm not worrying about the constants. So if there's extra terms, this is just a first order term,
Okay.
right? So you won't see a log n term. That's maybe the easiest answer. Right, unless it's a first order term. Okay. So what happens in between p equals to 0, p equals to 1? Well, truth is we don't know exactly what it happens. We didn't manage to do it, but well, there was yesterday, right? Guy Bressler talked about the statistical reductions. So here, in principle, you can use a statistical reduction. We used one. Maybe we were very, very conservative, and we just did a simple one. So the case s equals 1. We can do this reduction. We know that essentially p equals 0. It's harder than p equals 1. It's easier. It's an easier problem than p equals 1. So we can use this to get a lower bound. But for s greater than 1, we didn't manage to get a nice reduction. But to be very honest, I don't think we tried as hard as we should. Okay. But nevertheless, the two results into two extremes are about the same. So it's very hard to believe that something really interesting will happen in between, right? So we don't know what happens here, right? But we know essentially in the non-adaptive sensing case, in the small sample regime, right, we know that, well, essentially having a dynamic signal doesn't really help, right? It's or help or damage. You cannot see it so easily. And if you can see it, it could be static or dynamic, and you'll still be okay. So how about the rest here? What happens in the adaptive sensing case for, well, lower bounds, right? Maybe just say something very quickly about the proof of the theorem. So the proof of the theorem is somewhat standard, right? It's a truncated second moment method. So what you do, right, and probably most people here have seen proofs like this, right? So you lower bound the risk by essentially, or the sum of the type 1 and type 2 error by a function of the likelihood ratio, so the expectation under the null of the deviations of the likelihood ratio in 1, right? And then you just use, well, Cauchy-Schwarz or Jensen's inequality in this case, to use the variance of the likelihood ratio under the null to control that term. Right? The problem here in this case is that if you write the likelihood ratio, you have an expression like this. Looks complicated, but you have this term here, x of that term. Essentially, this is pretty much a constant. And this is the number of times your design hits the signal. Right? And depending on your design, this could be pretty nasty, right? So on average, this is going to be always somewhat small, like ms over n. But if your design is such that you are always measuring the same component, well, if you are lucky, right, you will get a huge amount of signal, right? So depending on the design, this will not concentrate well. So essentially, if you try to control the variance of this for all designs, you'll have a problem. So what you have to do is sort of remove from consideration the bad cases. So you construct an event and you tame the tails of the likelihood. You just truncate the tails, and you can get a similar bound like this if you don't remove much from the tails, but just enough to control the variance. And that's the truncated second moment method. So that's basically it. Okay, modulo all the technicalities that you have to deal with. Okay. How about the lower bounds for the adaptive sensing case? Well, for the static case, we know how things go. What happens if you are in the other extreme? Well, it's the sparse mixture case. We also know what's going on. So what happens in between? So for technical reasons, we are going just to focus on the case s equals 1. Right? And what you have is that, well, this is regardless of the dynamics, p equal the value of p. This is maybe the more interesting case. It tells you what you should expect to see, that the effect of the dynamics appears in this lower bound, right? Effectively, it tells you that necessary condition is that signal magnitude needs to scale like square root of p times log and p squared. Okay, this is the case s equals 1. So the only thing that's different between this case and that case is that there's this factor p squared there. Okay? And actually, this factor should be there, but not be p squared, but be just p. And if you look at the proof, you'll see why I'm stating that. Right? So essentially, if you try to take this from s equals 1 to s greater than 1, we conjecture, it's not, we don't have a proof that this should be the lower bound. Yeah. And good. So, and how do you prove this? Well, it's again a second, 5 minutes? Okay, I have plenty of time. Yes. So it's again a second moment, truncated second moment method. Of course, we have to take into account that now your design is adaptive, so this makes things a little bit more complicated. And this is why the case s equals 1 is useful, right? Because we can essentially decouple the signal as a kind of a concatenation of static signals, where the length of these static signals is random. Okay? And our proof crucially relies on this, right? And then essentially, well, the length of each of these segments, it cannot be very large. It cannot be larger than essentially 4 over p with high probability. So that's essentially what we do. Okay, and well, a few more things. So if s is greater than 1, I said that we didn't manage to do that, and even getting a reduction, a statistical reduction, seems to be maybe a little bit difficult because of this adaptivity of the design. But you can think of a, well, arguably simpler problem. That's, well, you just concatenate a bunch of one sparse signals, one on top of the other. That should be easier than the original problem, right? I didn't manage to formalize this heuristic, right? So to be very honest, it's extremely believable, but to get it really formalized, I didn't manage to do it. I would be happy if someone has a good idea how to do this. Okay? So essentially, we managed to fill out, well, a bit of the table, not everything, but a bit. And this is for the arbitrary sample regime. This is what we know, but this is not so interesting right now. And finally, well, we did some numerical experiments just to, as a sanity check, and you essentially, you see that this is signal strength parameterized in a reasonable way based on the bounds we have, and you see that, well, this adaptive method works, obviously, has a better performance in terms of risk than the non-adaptive one, especially if the dynamics are slow, right? Things don't change very fast. Okay? Good. Maybe the more important slide, the last one. Okay. So what happens if you have you are in the large sample regime? You actually make significantly more measurements than n over s, right? Then it becomes tricky because you are not going to, well, you should not do this adaptive sensing test I described, because you want to leverage out. Maybe you get some evidence that there's an active component here, and later on you get some extra evidence and you start pulling it all together, right? So you have to do something else, okay? And also in the non-adaptive sensing case, it's very unclear what's the right way to do things, right? And what's the effect of p in the problem difficulty. It will start appearing in the non-adaptive case as well. It will start helping, okay? And can you be parameter adaptive in this case? So right now our methods don't use any of the parameters except the sparsity s. That's still needed, although I think we can get away with it somehow. I think I should say s there, but yeah. Right. More interestingly, like the example I had with the graph, you want to look at situations where the dynamics are not just completely crazy like I described, but they are a bit more structured. If you are active at this time here, maybe your neighbors are going to be active. You are not just going to go somewhere else, right? So what happens in that case? It's not obvious how to do things. This robustification idea I described, it's also not very sensible. Right? So you have to do something else, right? You can also have other models where instead of an elevated mean, you also have an elevated variance. There was a reviewer of our paper that asked this, and we did some back-of-the-envelope calculations, and you can essentially do this. Maybe more interestingly, this was a question I got last week when I talked about this, is that what if your essential signal is reacting to the measurement? So they notice that you're listening, so they just move somewhere else, right? What can you do in that case? So this is important in the case of cybersecurity. When you're chasing the bad guys know they are being chased, they are going to move around. So how difficult is that problem? And well, that's pretty much what I wanted to say. So thank you very much.
Questions for Rui?
Yeah.
How crucial is the result depend on the specific generative model you assume the signal dynamics. If I assume that the change every time is at most a proportion p, but not necessarily this random way, does the upper bound still go through?
So if the signal, the dynamics of the...
Yeah, you're told that every time you'll change by a fraction of p. Not necessarily by coin flips in the way you described.
Well, depending on the dynamics, the upper bounds will change for sure. The lower bounds will also change. We consider these dynamics because it was the simplest thing we could think of. But if you have a very different dynamics, it might be different. For example, if you have structure, right? What might happen is that you might have just a little bit of evidence that there is a signal, right? But not enough yet to stop sampling. And then, well, you lost the signal, it kind of disappeared, but you know it should be, if it was there, it should be in the neighborhood. So then you will sample in the neighborhood. You are not just going to sample at random elsewhere. So I think then things change dramatically. And one thing that I didn't mention, but so if you're in the static case, one remarkable thing that happens is that even if your signal is sparse but has structure, let's say the activations are all in a contiguous block, like an interval, for adaptive sensing this doesn't make a difference. You cannot capitalize on structure if your signal class is relatively symmetric. But for non-adaptive sensing, this makes a huge difference. So there's this paper on combinatorial testing problems that works a lot, that kind of elaborates a lot on that. But surprisingly, if you are, well, maybe surprisingly, if you are doing adaptive sensing, the structure doesn't help. And the reason for that is that, well, if you have evidence that there's some activity in that component, you just keep measuring it until you gather enough evidence, or then you stop, and you just have to measure elsewhere.
Okay, yes, thank you.
Yeah, thank you.